Give us one moment. Okay. So it is my pleasure to be presenting to you today Blue Origin Scopes team, which is a CNC conformal coating machine. Our team is made up myself, Jacob Prisman, as well as Rowan Janssens, Joseph Gilbert, William Skelly, and Danny Burns. Our liaisons are Alan Tate, David, Federico, and Sarah, as well as our advisor, Lawrence, and a special thank you to Connor, who helped out with software for our project. So, our project is a CNC conformal coating rework machine. This is a semi-automatic robotic spray coating machine for simplifying and accelerating Blue Origin's current in-house PCB work process. PCB stands for printed circuit board. And printed circuit boards are the heart of the modern world. You find them everywhere, from inside of your smart devices like a phone, to an automobile, this very projector, and in our case, rockets that go into space. However, circuit boards can be damaged by many environmental factors. This includes dust, water, dirt, and particularly in space, something called tin whiskers that can grow between solder joints and cause many issues. So what is the solution? The solution is something called a conformal coating. Conformal coatings are protective coatings that seal off the electrical components from outside factors. They form a mechanical barrier that ensures that nothing can get in there and short components. However, sometimes this coating needs to come off. If there's an issue or they're doing testing on a board and they need to replace a component, they must remove the coating, and this can be done using a workstation that last year's Blue Origin Scope team made for the avionics team. However, after the coating is removed, it also needs to go back on for qualification testing and for further use of the board. Normally, this is either done by manual rework at Blue Origin, which is done with brushing, or it is sent off to a manufacturing facility to be done. So either, if it's done by a brush, it's inconsistent, or if it's sent off, it takes a whole lot of time, both of which are bad. So how will Blue Origin improve their conformal coating rework process? That's where our team comes in. So that was the task we were assigned. And our process started with industry visits, going to explore what the status quo is, learning about it, and learning what some of the issues are. We then defined our requirements, did architectural trade studies, prototyped our system, characterized our spray valves, and made a polished, finished machine. Starting with the industry visits, we found right off from the beginning that these machines can be really finicky and difficult to use. For example, we talked to one engineer who had spent 8 months working with a refurbished machine and still hadn't gotten it online, still was not making any money from the machine. And these machines exist. They can cost anywhere from $40,000 to $100,000, but they're designed for large volume production, and they can be difficult to use, and they're not designed for the specific sizing and requirements that Blue Origin has. So we start with top-level design trades, looking at what type of valve do we want. There's lots of them. There's some that microjet and shoot a thin stream down. There's some that spray from way up high, and we're going for something in between the two. A mid-level spray, it's a cone pattern, and it works great. The first semester, we focused on making a functional prototype. We created all of our fluid systems, all of our electrical systems, and we made sure that everything worked as it needed, and it allowed us to do a series of spray testing to characterize our valve and our system. We sprayed over 300 coupons, varying over 5 different variables that affect the quality of the spray. In the second semester, we worked to design and fabricate our refined system, create a comprehensive documentation package, and get ready to ship our completed system to Kent, Washington. So now, without further ado, the moment you all have been waiting for, I present to you our machine. And here is the wonderful Rowan Janssens to tell you all about it.
Thank you very much. All right, let's take this thing out of e-stop, and we can start talking specs. So our machine has a 24-inch by 24-inch spray area, which allows Blue Origin to coat even the largest PCBs that they have, or they can load this machine up with a bunch of smaller boards and coat them all in a single setup. Inside the machine, we have a modular PCB fixturing mechanism, which allows the operator to quickly set up the machine for a board of any shape or size. And that allows them to get the machine ready in a matter of minutes. Over here, we have reimagined the solvent workflow and the purging routines with a built-in solvent drawer. If you pair that with our quick change toolhead, it makes the whole process of swapping in and out the conformal coating cartridges and performing purge routines a really simple task. On this side of the machine, we actually have the control interface, which is comprised of both the analog control and our digital spray mapping software. The control panel features a direct control with the hardware and spray system, which gives the operator greater machine awareness and control. And then we have our digital interface with our custom user interface, where the operator can use simple geometry to quickly sketch their spray and avoid regions on an augmented reality image of the PCB captured in real time under UV lights, which allows you to see where the existing coating is and where it isn't. On the outside of the machine, we put a lot of thought into the ergonomics and the use. The door features gas springs for easy actuation and an adjustable stay, which allows an operator of any height to configure the machine to be operated to their comfort. The machine has built-in storage, which allows us to store various fixturing items and also different consumables that are used in the coating process. And finally, the machine has a built-in fume extraction system with quick swappable filters that allows the entire thing to operate in a lab environment without the need for additional air infrastructure. And it does all of this while staying within a 40-inch by 60-inch footprint. So let's talk about how this meets the needs of Blue Origin. Our machine leads to a 50% reduction in cost for these PCB rework operations and a 15% reduction in scheduling. That means that Blue Origin no longer has to spend their valuable time and money sending their boards back to the fabrication house for recoding. They can just do it in-house with our machine. In addition, our machine boasts improved coding consistency and repeatability, which means that you no longer have to worry about the variability introduced in a hand-applied brushed conformal coating. And finally, we believe that our streamlined user experience outperforms a lot of the other products that exist on the market today. And that's why we think our machine is the perfect solution for Blue Origin's problem. And we can't wait to tell you more about it at the poster session. Thank you.
Hello, we are the Boston Scientific Scope team here to present to you this year's project on the sustainability of the biopsy forceps product line. My name is Madeline. The rest of my team here is Lillian, Miriam, Cassandra, KD, and Kai. Endoscopies produce a massive amount of waste at approximately 2.1 kilograms per procedure. Now, this may not seem like much on its own until you realize that endoscopies are so ubiquitous that they are performed at a rate of millions of procedures per year. That 2.1 kilograms really adds up. As such, the goal of our team this year was to help Boston Scientific on the way to its goal of being completely carbon neutral by the year 2050, by breaking down and redesigning their forceps product line with the guiding principles of functionality and sustainability at the forefront of our minds. But let's take a step back. Before we get into the project itself, let's talk a little bit about what exactly an endoscopy entails. An endoscopy is a procedure which allows a doctor or technician to examine the interior of a patient's organs. It's performed using an endoscope, which is a long, flexible tube with a camera and a light on the end. Forceps, as you can see here, are devices often used as part of endoscopies to take tissue samples for biopsy. They have jaws for taking the tissue sample and are long and thin enough to fit down in the endoscope and be actuated by a handle which remains outside. To pinpoint which areas of the current design could benefit the most from new consideration, our first order of business was to perform a life cycle analysis of the carbon emissions from the forceps from their creation to their destruction. To do this, we broke down each component of the forceps, weighed them, and researched their materials to figure out how much carbon was emitted from their creation and their incineration. Furthermore, we worked with Boston Scientific to get data and calculate the impact from the transportation. The chart you see here is a synthesis of all that information. We discovered that the creation has by far the largest impact on the overall emissions, while transportation is nearly negligible. This life cycle analysis set the stage for the rest of our project, informing our design decisions and providing a framework by which we measured our success.
So as Madeline mentioned, when we were creating our LCA, we took the forceps product and broke it down into its individual components. From these components and the LCA, we were able to identify which components had the most CO2 production in the product, which turned out to be the handle, internal coil, internal wires, radial jaw, and the plastic packaging. During the fall semester, we focused on these 5 components, working on developing designs while also getting a better feeling and understanding of the forceps product itself. Then, at the beginning of the spring semester, we reassessed our designs and discovered that 2 focus areas had the most impact regarding reduction of CO2 emissions, and those were the handle and the internal coil. We then spent the rest of our spring semester refining those ideas. Of course, at the forefront of our designing process, we were thinking of sustainability, and we decided to divide sustainability into 3 design aspects: material, weight, and reusability. Material is important because if we can recycle a product and not have it incinerated, and incineration causes a lot of CO2 emissions, we can automatically remove the amount of CO2 emissions caused by destruction. Material is also important, though, because every material has a different amount of CO2 that it gives off. And if we can go ahead and switch out the material to be less CO2 content, then that's a good choice. Then we have the weights. So, of course, with weight, if you have a smaller design and it's lighter, you're going to have less material, so you're going to have less material being created and destroyed, and therefore less CO2. Weight is also important regarding transport, though. This is using the assumption that with a smaller product with less weight, fewer shipments would be needed in order to meet consumer demand. Last but not least, we have reusability, which is important because if we can make the entire product or even a singular component reusable, the amount of CO2 produced from it is astronomically cut, and this, out of the 3 design aspects, ended up being the most impactful. Of course, there were other design considerations other than sustainability that went into our developments. First, we looked at marketability. Is this design ready for the current market that Boston Scientific has? And if not, what steps are needed in order to get it ready for the market? There was cost. Is the cost difference going to be too much for Boston Scientific, and how does that cost affect their consumers? We have ergonomics. Is the design we created efficient for users and also comfortable? Functionality, which is important because we don't want to change the original function of the product. And then implementation. How long will it actually take before we can implement these designs in the real world? For our results, we ended up designing 3 products. 1 single-use design, which has a proposed 8% reduction of CO2 emissions from the forceps product line, and 2 reusable designs, which has a proposed 89% reduction in CO2 emissions. The creation of these designs is not only an amazing accomplishment for us as a team, but a great step towards Boston Scientific's 2050 goal of carbon neutrality. We want to thank all of you for being here, and a special thanks to our liaisons, Andrea, Rosanhel, Ryan, and Sam, and of course our faculty advisor, Jessica Townsend, and we hope to talk to you more during the poster session.